Thank you for allowing me to present in this way. I want to thank the organizers for putting together the symposium and Dr. Sorensen for the invitation. So I titled my presentation The Tale of Two Models because I sometimes am struck with the fact that in obesity and nutrition research, we talk about the best model or one model, and there's no really such thing because each model is an approximation of reality, and there's different use cases for these models. These are some of the things the models do that more than just predict. They might describe, they might explain, they might reveal structural relationship, they might enable counterfactual scenarios, address what-if questions, they might compare interventions, and depending on the use case, we want to develop models that make sense for that use case. And so that's why the tale of two models is quite interesting, because even though at the outset they appear like they are very similar, they both forecast, they have different use cases, primary use cases. I'm going to begin with the Lancet paper, which is for two reasons. One, it is not my paper. I did not co-author this. I led the authorship of the other paper in obesity, and I'm bored with it, so I found this more interesting because I could dig in. And the second reason is that it actually has more underneath the hood because they have so much data pre-processing and understanding that was required to do what they did. So it's interesting. I have handwritten notes on almost everything that I do where I first learn it. And I developed something called toy examples to understand pieces of the data analysis. So these slides they look like this. If you're interested in these slides, you can email me and I will send you the under the hood of the Lancet paper so you can better understand every aspect of it. But I took those handwritten notes and developed them into these slides to just give you a highlight. So in the paper, they predict prevalence, and they predict prevalence by state, and it's determined by where the birth year was. And you see these seemingly trajectories of forecast. Now, where did those forecasts come from? And this is not the only data that's in the paper. They also have outcomes of prevalence by buckets of age, region, state, and so forth, and other subpopulations. So where did they come from? Well, there were 134 sources of data, and these are just some of them that I listed up, the traditional NHANES, BRFSS, and so forth. And then they used that data to make those predictions, obviously, but they couldn't just drive forward and pull the data together because the outcome measurement of body mass index was measured differently. Some studies used self-report, some studies measured BMI. And so they picked the data that had both self-report and measured BMI, and they fit a regression model to predict the bias, the difference between self-report and measured BMI. Then they computed the residuals of the bias from actual bias versus bias that was from the residuals from the OLS model. And they assigned a threshold which they deemed unacceptable, so the outliers. And then they trimmed and downweighted the bias of the residuals that were beyond this this threshold. And they reran a new model with this downweighted bias and the non-downweighted biases together to come up with a new model. And in this way, corrected self-reported BMI. So in BRFSS, it's self-reported. So they took the self-reported BMI and then subtracted the model, the trimmed bias model, from that to correct for it. I went in detail for that because they did so much to treat the data, and I actually want to just show you one peek at how much they went to treat the data. But there's more, and I want to show you just one more thing, and then we'll go into their models. They also did not use the same, if they're concatenating two different data sets. One data set might have lots of data for one state, and one data set may have less data for one state. And because of that, you might end up with holes in the data so that you can't directly pool everything. So, under the assumption of a Gaussian distribution, they then, for state and year, they pooled the data by assuming this Gaussian distribution, and the places where you don't have data would be a hole. And you basically plug up the hole, and that's exactly what they did. How they did it was a little bit more complex than I'm making it sound, but that essentially is what they were doing, which was another set of computations. And so in something like this, where they're trying to fill in something, they would fill in this North Dakota by looking at data that was close, which is Montana's close to North Dakota, and I'm not randomly picking these states. I grew up in Montana, and my dad used to cross the border and work in North Dakota. But I fill in that missing data set using a kernel which assumes this Gaussian distribution. So that was just a little bit of what went into treatment of the data. Now we're getting to the models of prevalence. There were two methods they used. One is very straightforward in my opinion. So they basically took data from long past and then just ran a line through that to make a prediction. And in this case, my face is covering it up, but we're making a prediction in 2025. Or 2030, I think is, my face is covering up, so I can't see. It's 2030 that I'm making the prediction for. This black curve that you're looking at are the weighted slopes. So you do the weight, you could weight all the slopes evenly, you could weight the more recent slopes more. I was unclear how they weighted the slopes, but that is what they call the ensemble forecast. And you get the true prediction from all these weighted slopes by weighting them by using different secant lines. And I call this the Runge-Kutta analogy. So if you were in differential equations and never used numerical methods, you would have used something called Runge-Kutta, and that's how we weight slopes in Runge-Kutta. Very similar idea. One thing they did is they added a noise term to this linear prediction, and that noise term would be drawn from a normal distribution, and they would simulate this 1,000 times so that you get 1,000 different predictions of the 2030 prevalence, and then you would take the median as what you report in the paper with the confidence interval. The second approach they took was this, I named everything Bayesian, but it's a Bayesian, this is where they're using the Bayesian spline method. They look at the curves over time and make a decision about what that curve looks like. So their curves were complicated, so I made up a toy example with cookies eaten versus sock length so you can see what they're doing. That looks kind of like a cubic, so I'm going to assume that it has a functional form of a cubic. But I noticed that there's an inflection point at 5. As often common, we call it inflection points in math. In the terms of Bayesian splines, they call this a knot. So they define this knot, and they force that knot to happen by choosing that functional form. And then it's Bayesian because these beta 0, beta 1s, and beta 2s, they're chosen from priors. So we know something about the distribution of those parameters and we draw from it. Then you simulate plausible curves. So in this case, based off of that functional form I just gave you, and I can't remember what I did, but I made up some kind of prior that was completely made up, and I drew some plausible curves here. And all of them will have an inflection point at 5 inches of sock length, and they're making a prediction at 8 inches of sock length. And you'll see everything from the yellow curve up to the orange curve is a prediction of sock length at 8. And what you do is you run this 1,000 times. Now pretend it's not the sock length one because I don't need to draw the diagram, but you'd have something similar for prevalence curves with maybe more than one inflection point. And you would do this 1,000 times and get a prediction for each time for the prevalence at 2030, for example. And then you would get also your confidence interval for free because you have variation in the way you ran your simulations for these 1,000 times. The authors did this at the state level, the subpopulation levels in different buckets, and then generated the national prevalence level by putting all those buckets together. So that is how they came up with the Bayesian one. And then you could do whatever you want with these two methods. You could average them. It gives you two ways to put them together. You can compare them separately and look at them and see if there's a huge difference and then ask yourself why. So very careful data analysis treatment on this particular paper. All right, I'm pausing. And this is a recording, so it's going to be on YouTube, so you can rewatch this and actually hit the pause button so that you can force me not to talk as fast, which my students complain about. Differential equation model is quite different in its development. This is the paper from obesity, and the idea is that prevalence flows from one compartment to another. In the case of normal weight, for example, those individuals are susceptible to weight gain, a percentage of them, and they could flow into the weight gain cup of overweightness by either interacting with people that have overweight or obesity. They could spontaneously gain weight, maybe through a pregnancy, and thereby end up in the cup of overweight. And also, some of the folks from the overweight category could flow back by losing weight into the normal weight category. So everything is modeled by flows and rates of change, and so that's where we're using calculus. This flowchart appears in the manuscript, and it really just, the flowchart itself describes the model. You are flowing from one to the other. So here's one where we have susceptibles and bursts. There's a transition due to social interactions and non-social interactions, and you have deaths by every single category, and thereby create a whole system that's interacting with each other to generate a population-wide movement between one compartment to the other. This model includes parameters that are actually the birth rate, the proportion of births that are at higher risk for weight gain. So being born in an obesogenic environment, for example, would be a higher predisposition to weight gain. There's a time length involved to weight gain, so it's not immediate, you jump from one category to the other, so that's built in, this lag. There's a predisposition to weight regain. That means that if you've lost weight and ended up maybe back in the normal category, that you as a chunk, that population subchunk, is more apt to gain weight back. There are both social and non-social draws to obesity. Differential death rates was a very important thing that my collaborators felt should be in this paper, so it is, but I did show them later it doesn't have that much effect. And the outcome is prevalence predictions in all BMI classes for adults. By BMI classes, I mean normal, overweight, class 1, 2, and 3 obesity. That's what the differential equation system looks like. If you're not a differential equation modeler, that might look scary, but it actually is just a quasi-linear system of differential equations. It's not complicated and actually can be simulated pretty quickly these days on your cell phone, to be honest. What you get from that are trajectories. Differential equations yield entire curves as their solution. And so you can generate once you fit the parameters, and these parameters are fit using a shooting method from N. Haynes, and you can predict then and forecast 2030, that's as far as we went back then, and get these predictions of class 1, 2, and 3 obesity. And we also ran the same type of model for the UK because they had data available in their national surveys. One of the things that you see here is that a plateau is predicted. The functional form of the curve is not dictated ahead of time. So what you're seeing is the entire curve is an outcome. And so what happened is it looked like everything was plateauing. And we indeed proved using mathematics theory, there's theorems in the paper that prove that you will get this plateau. You can also run what if scenarios. What if the birth rate changes? Well, what you see is predictions are very sensitive on that parameter. So higher birth rates lead to lower plateaus, and lower birth rates lead to higher plateaus. On the other hand, one of the things you think should be really important, which is the predisposition to weight gain, when I toggle that parameter, there doesn't seem to be much movement on the curve. So it's not as sensitive to that particular parameter as it is to birth rate. There are a lot of differences in these models, and I'm not going to go through these one by one. I'll just ground you to a couple of them. The first one is the mathematical foundation. The Bayesian plus IHME, which is all the other stuff that goes with pre-processing. That particular one was developed as a data, the curve shape was dictated ahead of time, and then you use data to fit the parameters. On the other hand, the differential equation model was a system of ODEs that transitioned between compartments, and it needed no data to start simulating, which is kind of an odd thing if you're a data person. The timescale behavior, you see an equilibria plateau on the differential equation model. The trends on the Bayesian model are learned empirically. So you don't assume a long-term equilibrium, but you do assume the curve shape, as you can see from the curve shape row. There's different features. Like, for example, the Bayesian model needs lots of data. The differential equation actually needs none to start with. The granularity is very fine for the Bayesian model, but the granularity of inputs for the model, other models not, but could be extended, but it's not. There's no such thing as missing data for the differential equation model, the treatment, but for the Bayesian one, there is, and they had to think about that. The Bayesian model integrates covariates much better, but the differential equation model can only do so through parametric forms. What I call parameters, those are the weights on the Bayesian model. Those are more difficult to interpret, but the differential equation model has mechanistic meaning. So, for example, birth rate, we all know what that is. I can go to the census data, pull that number, it has meaning. This is the most important difference between these two models. There are use cases. The primary use case for the Bayesian model is forecasting with uncertainty at local levels. The differential equation model, on the other hand, it's for exploring mechanisms and what-if policy scenarios. So I can toggle one and see the effect on all the other predictions. The questions for those use cases are quite different. What will the prevalence be in 2035 in Colorado teens is a question that you could ask of the data Bayesian model. On the other hand, the differential equation models, the questions are, how does changing the birth rate affect the national obesity plateau? The interpretation of that, the Bayesian model is excellent for reporting trends, but it's more difficult for mechanistic inference. On the differential equation model, it's excellent for understanding drivers, but it's not really made for predicting trends, although it can. So, the uncertainty piece is I think one of the most valuable pieces you get from the Bayesian plus model. It handles uncertainties, and they built that in. The differential equation model is a purely deterministic model, and it doesn't really have uncertainty built in. So, with that, I am actually going to close. That was a lot of information. So, I will close with this last slide of strengths and limitations. Each model that you do, the use cases quite differ, but you have strengths and limitations with each one of them. And the strengths of the Bayesian model is this high resolution, uncertainty aware, very adaptable. The differential equation model's got mechanistic insight and can simulate hypotheticals without data. So I can tell you what different curve shapes there are just by simulating scenarios. The limitations of the Bayesian model are that it's harder to interpret mechanistically, and the curve shape is emergently. I had to decide that curve shape ahead of time is what I mean. The differential equation model, on the other hand, it's less granular, no built-in uncertainty, and less data adaptive. Each one's good for its good thing, a particular thing. The Bayesian type model is good for public health dashboards, high resolution stage by age forecasts, while the differential equation model is more for policy scenario testing and hypothesis generation. The Bayesian model is less good for explaining why prevalence changes, and the differential equation model is more local, is less good for making local level predictions. I do want to mention one last thing. I know David Allison's in the audience. One of the things I hear about these systems models is that there's causal language wrapped around it. And I think it's really, really important. And there should be something out there that kind of taps in and knock, knock. You cannot use those differential equation models for causal inference. Causal inference comes from causal inference models. And causal claims from these systems models should be tempered down. It should not be there. They're not causal models. And so I close with that. And one last thing, I want to thank you for your attention. And this is the sister I stayed behind to support, and she also thanks you as well. Thank you very much.